Hello everybody, and in this presentation we're going to be talking about more on induction, including indirect proofs, tautologies, contradictions, contingent propositions, and analogical reasoning. So first up, we will be talking about indirect proofs, what is called reductio ad absurdum. And what you do in a reductio is that you assume that what it is that you want to prove is false is true. Then you show that if what you want to disprove is true, then it leads to some sort of absurd conclusion. Okay, so here's a rather amusing example of a reductio ad absurdum, where Sheldon rather defines what a reductio is. So if you click on the little image there, and if you are using the PowerPoint file as opposed to watching this on YouTube, that will be your link. It will open up the video in a new browser screen, and you'll be able to watch the video. Then clicking back into this browser should restart the presentation. Otherwise, you will have to use a separate link. I'm going to pause for a couple seconds so that you can do that. But before that, it is worth noting that Sheldon does get something wrong. A reductio is not a fallacy. It is a method of argumentation. It is attempting to show that the conclusion one wishes to show is false leads to an absurd or clearly untrue conclusion and therefore cannot be true itself. Okay, I'm going to pause for a couple seconds so that you can click on the video. 3, 2, 1. Okay, tautologies. And here you can see a little cartoon where somebody is stating that the first rule of the tautology club is the first rule of the tautology club. This may give you some idea of what tautologies are. Tautologies are propositions that are logically or necessarily true. Here are some examples. Either Alice won the game or she did not. It is raining outside unless it isn't. One common form of tautology is the form P or not P. Another is P is B. There are many other possible forms. What they have in common is that they are necessarily true. There are also tightly tautological arguments as opposed to single propositions. These we later identify as the fallacy of circular reasoning or begging the question. It isn't that they are false, but that they are empty. Sometimes tautologies, even though redundant in some way, might be useful. It might be useful, for example, to say something like, either Larry lied to us or he did not lie. If he lied to us, then he was dishonest about what he said. If he did not lie to us, then he was incompetent regarding what he said. Either way, this does not speak well for Larry. In such a case, Larry either lied to us or did not lie to us is a tautology. It must be true, but it is strategically useful because it outlines two branches, two possibilities the arguer can logically follow to determine the result or conclusion of each. If you are in my ethics class, you will note that the Euthyphro argument begins with something like this when it asks, is a thing moral because God commands it, or does God command a thing because it is moral? In that case, Socrates is using a reductio by assuming that what Euthyphro is arguing for is true, that the good and what is commanded by the gods are identical, and then if one takes that as an assumption, then the question becomes a tautology. Those are the only two possibilities, assuming that one grants the original assumption, that the good and what God commands are identical. Back to single proposition tautologies. One might look at the statement, it is raining outside unless it isn't, and try to object by saying something like, well, couldn't it be in between? What if it is just sort of misty? But this doesn't really undo the tautology. As soon as you define what it means for it to rain, it is either raining or it is not. Since that one is of the form P or not P, we can see pretty quickly that we do not need to worry about the content of the statement to determine that it is necessarily true. Either P or not P is always tautological. So is P as P. Okay, contradictions. Contradictions are the exact opposite of a tautology. They are propositions that are not just false, but false by logical necessity. So here are some examples. Alice won the game and she didn't win the game. It's raining outside and it isn't raining outside. Now lots of times these look like this. P and not P. So you can't have something be true and not be true at the same time. This is called the law of non-contradiction. It is a basic rule of logic. They don't all look exactly like this. For example, here's one. There's an exception to every rule. You might have heard this before. But if it's a rule that there's an exception to every rule, then that means that there must be an exception to that rule. But if there's an exception to that rule, then there's a rule that there's no exception to. So if there's an exception to every rule, you end up with a contradiction. So it is important to check for contradictions in one's reasoning. Okay, contingent propositions. So we talked about tautologies, propositions that are necessarily true, and we talked about contradictions, which are propositions that are necessarily false. So what are we left with? Well, propositions are a particular kind of statement that can either be true or false. So the one remaining option are propositions that are neither necessarily true nor necessarily false. Instead, whether or not they are true or false depends upon some facts about the world. And these are the vast majority of propositions. Here are some examples. Brazil nuts are really seeds. Saturn is further away than Mars. Alice won the game. It is raining outside. Anything that really requires observation or measurement of some kind to verify is going to be a contingent proposition. Contingent propositions require the cooperation of the universe to be true. Arguments by analogy are inductive arguments. They are essentially saying that since two or more things are similar in some respects, they are also likely to be similar in some other respect or respects as well. So here is an example. I burned my finger once on a 350-degree cake pan when taking it out of the oven. Therefore, if I touch a cookie sheet currently baking in the oven, I will get burned as well. I'm drawing an analogy between the cake pan in the oven and the cookie sheet in the oven. I'm doing this based on the fact that they are both made out of metal, they are both in hot ovens, and properties that they have in common. In this case, the analogy is a pretty good one. It's pretty strong. Of course, this is induction. It could still be wrong. Maybe I was granted the superpowers in the meantime. Maybe the cookie sheet was just placed in the oven and hasn't had a chance to heat up yet, even though the oven itself is 350 degrees. The basic idea of an argument from analogy is that one says that two or more things are alike in some respect or set of respects, and then draws the conclusion that they are alike in some other respect or respects based on the fact that they are alike in those other ways. But one needs to be careful because not all analogies are good ones. If instead I was talking about a piece of styrofoam heated to 350 degrees and compare that to a cookie sheet, even though the styrofoam is something in an oven and heated to 350 degrees, if I touched it, I likely would not be burned. Or at least not very badly, because it doesn't transfer heat the same way that metal does, even though it's the same temperature. And in fact, this is why firewalkers can walk on hot coals for brief periods of time without getting burned, because certain wood chips, when they are laid flat, don't conduct heat very well. However, if you were to put aluminum foil or something over those coals, then those people would get scalded very badly. A statistical induction is an argument that since a particular percentage of a sample population has a certain property or properties, a similar percentage of the overall group does as well. Here's an example, and I'm just making these numbers up. Suppose that there was the following study. Out of 2,000 people surveyed in the US, 800 of them could swim. So 40% of the US population roughly can swim. As a statistical induction, if we have a random sample of the population, this is probably pretty good. I mean, the math works out. If we grab 2,000 people, that's a decent sample size. One thing to note is that you do not need to continue to expand your sample size with larger populations if there are no other confounding factors. This is a good sample size with about 350 million people in the US, or if there were 2 billion people in the US, so long as there are no other confounding factors. To see why, imagine that you are trying to see what percentage of jelly beans in an opaque bag are red versus green. Suppose that this is a large shopping bag with 20,000 or so jelly beans in it. If you took out 200 completely random jelly beans, you would have a pretty good idea of the percentage of red versus green beans. Now imagine that instead of a shopping bag with 20,000 jelly beans, you had a swimming pool full of 2 million jelly beans. Still, if you took out 200 completely random jelly beans, you're going to get a good sample. Of course, the key here is that the beans in each case need to be taken out randomly. If all of one color are at the top or all of one color are at the bottom, and you took beans from the top only, then that would throw off your results. So too with the case of the swimmers. This is why too small of a sample is problematic. If we had a sample of only one person, that person might have come from Hawaii, where there's much greater percentage of the population that is likely to swim than in Nebraska or Alaska. If we had a sample of just 2 or just 10, we could easily get a strange concentration in such states. But with a reasonably large sample, and if that sample is random, we can make a reasonably good inference, that is to say induction, regarding the percentage of swimmers in the general population. And that is the end of this presentation. I'll talk to you next time.